All right, part 2 of chapter 8. So in part 1, we talked about the composition of the Jovian planets and their interior composition, which were mostly hydrogen and helium. In part 2, we're going to go over their moons and their features. All right, what are we going to learn is what kind of moons orbit the Jovian planets. Why are Jupiter's Galilean moons geologically active? And what geological activity do we see on Titan and other moons? Why are Jovian planets' moons more geologically active than the small rocky planets? So these are the 4 main things that we hope to cover. I hope that you will be able to answer these 4 questions by the end of part 2. Now, what kind of moons orbit the Jovian planets? Now, these are the 4 most famous moons of Jupiter: Io, Europa, Ganymede, and Callisto. And if you don't remember them, just remember I eat green corn. So Io, Europa, Ganymede, and Callisto. So if you remember that, you will be able to remember these 4 moons. Now, Galileo observed some of the Jupiter's moons, and in fact, this is the what he had back then. The first solar system object invisible to the naked eye was observed by Galileo. Remember the magnitude system? So the magnitude 1 is we divided everything that we see in the sky into 6 different magnitudes. Magnitude 1 is the brightest star. Magnitude 6 is the faintest star. Now, these moons or satellites of the Jupiter are not visible. They're not visible to the naked eye, so you need a telescope. And so Galileo made the first observations of the invisible to naked eye objects of the solar system. And he said they must revolve around Jupiter the same way Moon revolves around Earth. Let's take a look at size of these moons and satellites. So we consider a small size or small moons if they are less than 300 kilometers, and we consider that being no geological active. The medium-sized moons are 300 to 1500 kilometers, and they had the geological activity in the past. And large moons that are more than 1500 kilometers, they have the ongoing geological activity. So this is the list of the most important satellites of these Jovian planets. So Io, Europa, Ganymede, and Callisto for Jupiter, the most famous ones. For Saturn is Triton, right here. For Uranus, the most famous ones are Miranda and Tatiana. The Neptune, the most famous one is Triton. And just to compare, these are the Mercury, Moon, and Pluto. In fact, one of the reasons that Pluto is not one of our, one of the planets, and we consider it as a dwarf planet, is because of its size. It is very small compared to the rest of the planets, and it's also small compared to these moons of the gaseous or Jovian planets. So the most important thing about these moons is that they have enough self-gravity to be spherical. Remember, if they're not big enough or they're not massive enough, they won't have a spherical shape. They have a substantial amount of ice, and they form an orbit around the Jovian planets. They have a circular orbit in the same direction as the planet's rotation. So if we have a planet rotating counterclockwise, the moons are also rotating in the same direction as their planet, okay? Now, what if they were smaller? So remember here, I said that enough self-gravity to be spherical. So Titan is spherical because of this. Moon is spherical because of enough self-gravity. Io is spherical because of enough self-gravity. Okay, if the gravity is not enough, they won't have a spherical shape. So, you know, they are about the size of 100, for example, these ones we have 22 kilometers. It's not big enough to have the self-gravity. 180 kilometers, 220 kilometers, they're not big enough to, you know, create self-gravity. And so that's why we call them potato-shaped. They're looking like potatoes. They're not spherical. Now let's take a look at the 4 Galilean moons of Jupiter. Io's volcanic activity. Io is the biggest, you know, the most moon or, you know, object in the solar system that has many, more than 100 active volcanoes at its surface. Now, remember, it's in the entire solar system. It does not have the biggest volcano. The biggest volcano is at Mars. Remember chapter 7? But it is the most volcanically active body in the solar system. Io is the most volcanically active body in the solar system. Why is that? So just by looking at the Io, as I said, it has many active volcanoes, and they're creating these SO2, S is sulfur, okay? There are more than 100 volcanoes. And the surface is the youngest surface. It can change in a matter of few weeks. So the whole surface of Io, or this satellite of Jupiter, can change in a matter of, you know, very shortly, in a matter of just few weeks. It has no craters, even though there are impacts by asteroids. They will fill in too fast. Io has the youngest surface of any object in the whole solar system. Now, the question is, so what I just told you means that it is geologically active, okay? It's not like our moon, or it's not like Mercury that's dead. It is like Earth, it's active. But Io is very small. Take a look at the previous slide. Io is right here. It's small. It's just like the size of the moon, right? So this is Io, this is moon. If that's the case, why is it Io is small? Small bodies cool quickly, so it should be dead. Do you remember the ratio that we talked about in chapter 7? Do you remember the 3 to R ratio? If you have a big R and a big radius, okay, we consider this to be the radius of Io. If you have a big R, this whole ratio is small. And that means the planet or the moon will cool down slower. But this R for Io is not big. It is not big. It is in fact very small. And that means this ratio is big. And that means that the Io should cool down way faster, very quickly, and should be dead by now. But why is it not? Why is it still geologically active? So in order to understand, we send a Voyager. We send a spacecraft, space probe. So Voyager 1 take a look at these volcanic activities, and it noticed that it is very close to the Jupiter, and also experienced a huge gravitational force from Europa. So the tidal forces are huge and provide an energy for these volcanoes. So if I ask you in an exam why Io is still geologically active, the very short answer to that question is it is geologically active because of the tidal forces, okay? Both from Jupiter and from Europa. It is active enough that in a matter of just few weeks, a volcano can be created in the surface, okay? Its orbit is also very highly elliptical, okay? So the closer that you're getting to Jupiter, the stronger the tides are. The further from Jupiter, the weaker the tides are. So flexes on the moon or the satellite creates friction. Friction creates heat. Heat creates volcanic activities. Okay, let me stop sharing and I'll show you a little bit of an animation to exactly understand the tidal heating. I'm certain that you haven't seen this before, but if you have, just bear with me in a little bit. I'm gonna explain what the tidal heating means in a little bit of a animation. So let me stop sharing my screen and then going back and share this screen with you. Okay, so you're seeing this now. So let's take a look at what I mean by the tidal heating. So this is Io, okay, and this is Jupiter. And the first thing that you notice is that it has a elliptical orbit. Now, let me show you the force. So this surface that is closer to the Jupiter is experiencing more force compared to the other surface. So as it is getting close, see this surface area, this arrow is bigger because this area is actually experiencing more gravity compared to the other side of the moon. This is a #1 trigger to cause these geological activity on the surface of the Io. Even though it's very small, but the tidal force will, rotate whatever that's inside, will create a rapid rotation or convections inside the Io's core and creating these volcanic activities on its surface. Okay. The other very most important thing, and I'll get to that in the PowerPoint as well, but since I'm here, I'm going to show it to you, that we have orbital resonance of these Galilean moons of Jupiter. So we have Ganymede as green. This is Ganymede. We have Europa, this in the middle one, and we have Io. And every 7 days, they line up in their orbit. Okay, so when the Io is rotating 4 times, the Europa is rotating 2 times, and the Ganymede is rotating 1 time, they line up. And that happens every 7 days. And you can actually see this as they line up, they'll blink. Take a look at right now. Did you see that all 3 of them just blink at the same time? So that is also causing their orbit to be elliptical, highly elliptical, because they all line up, the gravity will add up and creating these effects. Okay, going back to the PowerPoint. Okay. Io's volcanic activities. I'll go back to the animation to show you something else as well, but let's move on, and then we'll go back to the the animation one more time. Now, tidal heating, as we just talked about it. So Io's elliptical orbit means continual change in the strength and direction of the tidal force from Jupiter. So here, as we just said, we have a huge gravity pulling this side, okay, right here. The gravity here is way more than the gravity here. So I have a strong force of gravity acting on this side compared to this side. And this is causing the geological activity inside the Io. Over here, since they are pretty far away, they're pretty much the same. The force here and the force here are pretty much the same. Okay, so in other words, Io's is squeezed and stretched as it orbits Jupiter. But why is its orbit is so elliptical, as we just talked about it in the animation? So there is something called orbital resonance. We just saw it. It happens every 7 days. In other words, every 7 days, these three moons will line up exactly in this configuration. And that means it creates a lot of gravity, a lot of tugs. That means all of these orbits will slightly be elliptical, which is, by the way, not shown here in this video, in this little figure in this picture, but once they line up, because of the gravity, their orbit will be elliptical. So the tugs add up over time, making all three orbits elliptical. So let me go back to that thing that I just said. I'm gonna stop sharing the screen with you and going here. Share screen. Okay, so you're seeing my browser now. By the way, I'm gonna upload these features on Blackboard, so you have the full access to those. So this is the infrared image of the Io. Remember, the infrared, we can see perfect heat sources. And so these are the active volcanoes on the Io surface. If I go to the visible image, look like that. So these are the active volcanoes from infrared image. I just want to show you this because it's pretty cool. And as I said, I'm going to upload those on Blackboard, so you have full access to these animations and you can play with them if you want. Europa's ocean, a Waterworld. So let's talk about Europa. So we believe that Europa has an ocean, actually a very warm ocean underneath because of these tidal forces. Remember, these tidal forces create what we have on Io, of volcanic activities on Io. In the same manner, they can cause the interior of the Europa to heat up. And then what we see on the surface of Io is these ices on the surface of Io is being cracked. And the reason is the exact same reason for Io's volcanic activity. It's because of a tidal force. So ocean occasionally breaks through, flat surface, and the surface of the Europa is actually pretty young. It's about 10 million years old. So the most important feature of Europa is that it has an ocean underneath, a very thick layer of ice. So if you're looking at the interior composition, we have a metallic core, and then we have a rocky interior, and then we have a layer of water covered with ice. And these ice are cracked, okay, because of those tidal friction that we just talked about it. Ganymede. Ganymede is the largest moon in the entire solar system. It's even bigger than Mercury. Okay, Mercury is the closest planet to the sun, but Ganymede is even bigger than Mercury. There are clear evidence of geological activity and tidal heating on the surface of Ganymede. When we're looking at, okay, let me get rid of this panel up here so I can see the slide. Perfect. Okay, when we're looking at the Ganymede, there are some craters on Ganymede. Take a look at this flat big one. It is a crater, but it's been flat, okay? This big one has also been flat. It's not like these little ones that you can see in this picture. They have been, removed. So ice got a slushy and then couldn't maintain crater walls. So that's why they're gone. These walls are gone. All right. Now the caldera on Ganymede, where the subsurface liquid has drained away, it means that it has some sort of a evidence of a liquid water in the past. So Ganymede is one of the other than Europa, is one of the other moons of Jupiter that has a history of water in its past, and it's because of these evidence that we see in this picture. Okay, so caldera on Ganymede showing us the history of water, existence of a liquid water and its history. Callisto, very interesting. It is a classic crater ice ball, and there's no tidal heating, no orbital resonance for this moon. So if I ask you how many moons are involved in the tidal heating, you have to be able to name everything other than Callisto. Okay, so Io, Europa, and Ganymede. And very interesting, even though it is not having the orbital resonance, even though it's not geologically active, it has magnetic field. So it is covered with craters. So the surface is old. It means it does not have active volcanoes to cover and fill these craters. But why are these craters bright? So these bright spots are the leftovers, or the areas of the impacts of comets and meteoroids, but by why we see them as bright. The surface is dirty. The comets and asteroids and meteors punch through the dirty surface to clean ice beneath. So all of these very bright areas are actually the ice. So that's why they look like bright, but the surface is really old and dirty and dark. That's a close-up image of Callisto's surface, just to give you an idea how it looks. And a thought question for you: how does Io get heated by Jupiter? Take a look at this question. Think about it. A couple seconds. How does Io get heated by Jupiter? The answer is C, because Jupiter pulls harder on one side than the other. It's called tidal heating. We just talked about it, and I'll show you a video about it, right? An animation about it. So the gravity pulls stronger on one side than the other, and that is caused the interior of Io to be moving around and causing these geological activity on the surface. So we covered everything on Jupiter. Now we're going to Saturn. Saturn's moons, Titan. Okay, Titan has been known for many years to have the atmosphere thicker and denser than Earth, mostly nitrogen and argon. Remember, whether a molecule can be retained depends on three things. 1, gravity, the mass of the body, mass of the planet. 2, mass of the molecule. 3, speed of a molecule or temperature. Okay, Titan is really cold and makes the surface impossible to see. So it is covered with a very thick, very, very thick atmosphere. Okay. In fact, it's the only moon in the solar system that has a very thicker than Earth atmosphere. And it consists mostly of nitrogen with some argon, methane, and ethane. So this bluish green color that you see in the atmosphere is because of the existence of CH4 or methane in its atmosphere. So we sent a space probe in 2005 successfully landed on Titan, and it showed that there are existence of the liquid methane rocks in the surface of the Titan. So I'm going to share another screen with you to take a look at the landing of the space probe. Let's see. Okay, might be able to see this now. So this is the space probe Huygens landing on the Titan. And I'm going to share this with you. By the way, as I said, I'm going to upload these on Blackboard so you have a full access to it. So take a look at this. This is the landing of this space probe on the surface of Titan. And I'm gonna not say anything for as long as this video is playing. So don't think that there's something wrong with your internet, because this is a very slow process. So let's go. So as I said, the atmosphere is thick, right? So that means it will take a while to go to the surface. So right now it's getting close to land on the surface. And once it landed, I want you to pay attention to the features on the surface. Okay. So let's go to the PowerPoint again. Awesome. So as I said, these Huygens probe provided the first look at Titan's surface in the early 2005. It had liquid methane, rocks made of ice. So maybe liquid methane and methanol, ethane, C2H6, ocean. So there might be some sort of an indications of those. And I think in the next slide, I'll show you a lake of liquid CH4. So these new images from Cassini mission to Saturn show some methane rivers right here. And then let's take a look at this, Titan's lake. This is the radar image of Titan's surface, has revealed dark, smooth regions that may look like a lake of methane. So this is exactly looking like a lake on Earth, but on Titan, it does not have water. It's a lake of CH4. Moons of Uranus and Neptune, they also have, as I said, moons, and Tatiana and Miranda are the most famous moons. And for Uranus and for Neptune, it is Triton. So Just moving on. For Uranus, we have a varying amount of geological activity. When it comes to their moon, Miranda has a large tectonic feature and few craters. So that means that there has to be an episode of a tidal heating in the past when you're looking at these. Neptune's moon Triton, which looked like a cantaloupe, it is similar to Pluto in size, but a little bit maybe larger. And there is some evidence of a past geological activity on its surface. Now, Triton, which is the moon of Neptune, orbits less than 6 days, and its orbit clockwise. So, it also has the atmosphere of nitrogen and methane, but not very dense. So these black lines due to the sunlight covering methane. So as soon as that we have the sunlight, react with the methane, it will create a either bluish, depending on the conditions, either bluish color, which we see on the surface of Neptune and Uranus, but also it will create a blackish kind of environment, and it's the exact same process that made particles in the ring. Now, nitrogen, CH4, CO ice on the surface, possibly water and ammonia volcanism too on Triton. So now we don't really know the source of the energy and the source of the the cause of the force of deriving activities on the Triton, but Neptune's system was disturbed long ago to give weird orbits. Possibly Triton was captured very recently, and then the tidal interactions with Neptune heated up. So now the last part of our chapter, chapter 8, we're going to talk about why our Jovian planets, moons, are more geological active than the small rocky planets. Remember, Mercury is dead. Our moon is dead. Venus has very low geological activity. Mars does not have that much of activity anymore. You're all dead. The only planet that has the current activity is Earth when it comes to terrestrial planets. But when you're looking at the moons of these Jovian planets or the icy planets, they are more geological active compared to terrestrial planets. Why is that? So rocky planets versus icy moons. When it comes to the rocky planets, rock melts at higher temperature. First. Second, only large rocky planets have enough heat for activity. But when it comes to the ice or the moons, ice melts at a lower temperature, but tidal heating can melt interior ice, driving the activity. So the main number one reason that we see that the geological activities of a lot of active volcanoes on these moons of the Jovian planets is because tidal heating are more imprinted on those compared to when it comes to terrestrial planets. So what have we learned? What kind of moons orbit the Jovian planets? Moons of many different size. Levels of geological activity depends on the size, okay? The other thing that we'll learn is that why are Jupiter's Galilean moons geologically active? As I said, we just talked about it, tidal heating drives activity, leading to Ios, volcanoes, and ice geology on the other moons. Okay, so tidal heating. Remember, one side is being pulled harder by the gravity compared to the other side. What geological activity do we see on Titan and other moons? So Titan is the only moon with a thick atmosphere. Many other icy moons show signs of geological activity. Why are Jovian planets' moons are more geologically active than the small rocky planets? Ice melts and deforms at lower temperature, enabling tidal heating to drive the activity. Again, tidal heating is the #1 reason. Jovian planets' rings. So it's probably we're in the home stretch for the chapter 8, but we're going to talk about the rings of these 4 Jovian planets. So our goals of the learning for this little part is that what are Saturn's rings like? Why do the Jovian planets have rings? So we're looking at, for example, Saturn's rings. They are made up of enormous and tiny individual particles. They orbit over Saturn's equator, so they're in the center of, they're orbiting around the center of the planet, and they are very, very tiny. Here's a reason. So all of these little small objects, okay, they're rotating around Saturn, but the tidal force near the planets prevent the small moonlets or small particles to accrete into larger moons. What do I mean by that? Is that too technical? I don't think so. You know what the accretion means. Accretion is an upward process. You start by sticking, grains, and you build up to pebbles, rocks, boulders, so on and so forth, bigger and bigger. Now, the tidal heating prevent these particles to stick together and create a bigger moon. These moonlets occasionally disrupted by the impacts, okay? The ongoing impact is happening in all directions. So ongoing small particles blast off dust and debris to form the ring. So eventually all of these little objects will be, destroyed and turned to very small pieces, all rotating Saturn with the same rate in a stable orbit. So if you're looking at the ring, this is going to be what you see in your telescope, the Earth-based view. And if you're sending in spacecraft, it should look like something like this. So as I said, all Jovian planets have rings. The ring system of Saturn is large, complex, easy to see from the Earth. Let me take a look at this. So if this is rings of the Saturn, the most important feature is that we have 2 gaps. This little one here is called Anki gap, and then we have a division, which is Cassini division. This division is dividing the ring to 2 parts. Part 1 is A ring, which is this one right here, A ring. If you go over the division, you end up with a B and C ring, okay? The B ring is the biggest ring of Saturn. So as we just talked about, they are debris, and they are microscopic particles all rotating around Saturn with the same rate, and very difficult to see them if you're looking at them on the edge. So if you're looking at Saturn and you see something like this, it's very difficult to see the ring. But a few months later, in a different condition for the observation, in a different location, you might see something like this. Remember, the rings are always around the equator. The rings are always having the same configuration, the same position with respect to the Saturn. But since Saturn is moving very slowly over time, take a look at this, 1980, 1987, 1995, 2003, go back, so on and so forth. So it'll take a long time to do one complete rotation. In the meantime, it will take only 1 year for Earth to rotate. We have to take into account 2 more things. One is that we have the axis rotation, axis tilt, 23.5 degrees for Earth. We have the same axis tilt. We have axis tilt for Saturn. I don't remember from top of my head what the degree for the tilt is for Saturn, but there is a tilt in the axis for Saturn as well. Okay, now not all the circumstances for observing Saturn is the best. if you want to see the ring, okay? If you, I've talked about it in my observational astronomy class. If you want to see the ring of a Saturn, the best filter to use with your telescope is the green filter. But the ring will always have the same relative position with respect to the Saturn, but depending on when you're looking at the Saturn, when you're observing the Saturn, you might see either the edge, or you might be able to see the actual ring. So how did the ring form? So we have something called Rouchy limit. This is where the tidal force of the planet are too strong for a moon to survive. Okay, so let's take a look at this. This is a satellite, okay, and it's way over that limit. As you get closer and closer, as you get closer to Saturn, the tidal force on this part, okay, right, the tidal force here is way more than here. This area is closer to Saturn, so it is experiencing more gravity compared to this side. So I have a huge gravity here and a little gravity here. This means that the satellite or the moon will be turned apart, turned to small pieces like this, going towards the Saturn and ending up being part of its ring. So the red side of the moon experiences a stronger gravitational pull compared to purple side. And I have the exact same thing that I just talked about in red. If the difference between the gravitational force on the front and the back of the moon is greater than the forces holding the moon together, it will break apart. Okay, so Jupiter is also has a ring, some sort of a ring. It's very faint. It's discovered by Voyager 1 in 1979, and it's mostly microscopic dust, and they're really dark. Now, in case of a Jupiter's ring, dust is probably coming from the small moon's impacts. So the impacts of meteors or asteroids on the moons, creating these blast of particles and dust going to the space, then they're going to eventually be captured by the Jupiter's huge gravity, forming a dust-shaped ring around Jupiter. This is a spacecraft view of a ring gap of Saturn. Now, since we haven't, have a clear image or, the best image of ring, we have an artistic concept of the close-up. So these are little particles being, close to one another, but they're still trapped around, these either Jupiter or Saturn. So particles clumps together because of the gravity, but small random velocities cause collisions that break them apart. Uranus ring. It's faint, narrow, darker than coal. When the sunlight, as we just talked about it, when sunlight interacts with CH4, it produces a dark goo. It produces a dark material. And how do we know that? So it's through a process called occultation, meaning that when I have a ring or these materials, some of them are bigger, some of them are smaller. When I am looking at Uranus and I'm looking at its intensity of light being, kind of a constant throughout the observation, right? Now there are these dips in intensity, meaning something is covering the flux that's coming to us, the intensity that's coming to us, okay? So that is cause it to blink. And that's how we know that it has a ring. Okay? It's again very dark and it's very narrow and faint. So all four Jovian planets have ring system. Other have ring particles that are smaller and darker than Saturn. Jupiter has a ring, dusty materials because of the impact. Saturn has a ring, icy materials, microscopic materials. Uranus and Neptune both have rings. In case of Uranus, it's methane will create a dark material when it interact with sunlight. So why do the Jovian planets have rings again? They form from dust crater and impacts and moons orbiting those planets. How do we know this? Rings aren't leftovers. This is one of the other most important thing about this little part. Rings are not. So I wanted to emphasize this. So pay attention to this. Rings are not leftovers from planet formations because the particles are too small to survive this long. The planet formed 4.6 billion years ago. How much? 4.6 billion years ago. So these particles are very small. They won't be able to survive this long. There must be a continuous replacement of these tiny particles, okay? An impact happen will create a blast of materials to the space. They'll be trapped by the gravity, a huge gravity of either Saturn or Jupiter, Uranus, or Neptune. The most likely source is impacts, as I just said, with the Jovian moons. And let's take a look at what we've learned. So what are Saturn's rings like? They are made up of the countless individuals or icy particles, millions of particles. They're extremely thin with many gaps. The most important ones was Cassini gap. Okay, what was the other one? Yankee gap, exactly. So why do Jovian planets have rings? A ring system and other Jovian planets are much fainter with smaller, darker, less numerous particles. Ring particles are probably debris from moons. So this is end of chapter 8. In chapter 7, we talked about terrestrial planets. In this chapter, chapter 8, we talked about Jovian planets, and we covered the features of their moons and why they're geologically active. We also talked about their rings. So if you have any questions, email me. I'm going to post the homework related to chapter 8, and stay safe.